Okay, yeah, thank you. Good afternoon, everybody. We're very pleased to have Dr. Riajul Haque giving a talk today. He's a postdoctoral fellow at the Indian Statistical Institute, and he is hopefully going to join us as a postdoctoral fellow next year. And he's been working with a lot of people. The one that I know very well is Jan Mambrini, and I know you've been working on primordial black holes. I'm very excited to hear about your research. So please go ahead, Riajul.
Okay, thank you, Professor Venestas, for the introduction. I'm Riajul. I'm a current postdoctoral fellow at the Physics and Applied Mathematics Unit, Indian Statistical Institute, Kolkata. And thank you, Professor Venestas, for giving me the opportunity to talk here. So I will talk about decoding the physics of the early universe through primordial black hole, dark matter, and gravitation. So this talk will be based on these 5 references, and those work has been done is in collaboration with the Shubhashish. He's a PhD now at IIT Madras, working with Professor Sriram Kumar. And the Donald is, I think, a postdoctoral fellow at IIT Madras. The Nilanjan, he's a kind of postdoc at ICT PFP, and Ian Mambrini, the faculty at IJC Lab, University of Sackett, that is Sackett, and my supervisor, Devaprasad. So in my talk, actually, I try to motivate that what are the observational difficulties in the early universe and how we decode this phase of the reheating through observables like the gravitational or the dark matter. So first of all, I first start my talk with the observational difficulties in the early universe and introduce the background dynamics of reheating. Specifically, I will talk about the perturbative reheating scenario. Then I move my discussion towards the possibilities of the primordial black hole reheating. So what is that? It is possible that primordial black hole can form at a very early universe after the inflation during this reheating era or during the standard radiation domination. And if it is formed during standard radiation domination, then it is possible that that can evaporate and produce the standard model particles. So these possibilities will explore that named as primordial black hole reheating. And then we compare our result because at the start point, we'll discuss only for the monochromatic mass distribution, because for the black hole, we can take the monochromatic mass function, or in some cases, it will be the extended one. But at the initial start, I will discuss only for the monochromatic mass function. Then I will extend my discussion towards the extended one. So what will be the difference if one consider the extended mass function? Okay. So once I finish the scenario of reheating the production of the standard model particles through evaporation, I will talk about the particle production from the single black holes. So mainly, I'll talk about the pure standard model particle production, like the dark matter, or the right-handed neutrino can also produce there through the evaporation process. But I am not getting into that. I'm only concerned about the dark matter from evaporating black holes. Then I'll move my discussion towards the decoding this early universe space through gravitation. So there may be the one gravitational will be there. This is the primary one. So what is the primary mean? The primary mean, I talk about the tensor perturbations, which basically generate the vacuum fluctuation during this inflation. And if we just evolve the tensor perturbation epoch by epoch and finally calculate today, so what will be the relic and how this relic depend on the early history of the universe. So first I talk about this, and I'll try to decode this phase through different present and future gravitational observations like LISA, ET, and so on. And then I'll constrain this reheating phase through the scalar-induced secondary gravitation. Actually, I'm talking about the primordial black hole formation. So this primordial black hole formation is generally one of the possible mechanisms associated with it is the ultrasolar kind of model. So this ultrasolar kind of model leads to a scalar-induced gravitation. So I'll talk if the induced one, this scalar perturbation, it can be sourced the tensor perturbation at the second order. And what will happen if we analyze this induced gravitational wave and compare the data with the nanograph, compare the result with the nanograph 15 years data. And then finally, I'll talk about the quantum correction on the Hawking evaporation. That may be possible that quantum correction in the evaporation process leads to some interesting phenomenological studies like now the ultralight black hole can be stable, and there are their new mass window will open due to that. And finally, I conclude. Okay, so move to the first thing that what are the observational challenges in probing the early universe? So our knowledge about the cosmic history of the universe is based on two major observations. So one is the CMB, the cosmic microwave background, and the other one have the Big Bang hypothesis. The CMB basically predicts that there should be an inflationary phase with not inflation, there should be accelerated phase in the early universe, which can be made by inflation, can be named as inflation, and the energy scale is of the order of 10 to the power 15 to 10 to the power 16 G. And if you talk about the time scale, so if the time scale is around 10 to the power minus 36 seconds, around. And if you talk about the Big Bang electrosynthesis, it basically predicts the quantities such as the light element abundance. And the energy scale around 1 MeV, and the time scale is around 1 second. So you can see there is a massive gap in terms of energy and the time scale between the end of the inflation and the BBM. So that is that section is poorly understood from both the theory and the observational point of view. So here, basically, this reheating dynamics lies because after the inflation, what happens? We have to get rid from that inflation. Because inflaton then decays into all the standard model particles because finally we need a radiation-dominated universe for the Big Bang universe. So this here basically this reheating dynamics lies. The inflaton field rolls down at the minimum of the potential, and inflaton oscillates. And what happened at that point, if the amplitude of the oscillations is quite high, so there some resonance kind of production happen. Or if the amplitude after subsequent stage, when the amplitude of oscillation is quite low, we can use the perturbative. So basically here the inflaton decays into all the standard model particles or dark matter and everything. So the empty space is filled up with the entropy, right? Because all the entropy is generated during this phase. So now I just give a brief overview of this reheating dynamics. And at the initial stage of the reheating, what happened? That the inflaton field oscillates, and the amplitude of the oscillation is quite high. This resonance kind of production we cannot ignore. But there are some problems. Even for the resonance kind of production, the non-perturbative treatment of this reheating analysis, and there we cannot get rid of the entire inflaton. If your if inflaton oscillates at the minima, it's like the phi square kind of behavior at the minimum. Then we need a perturbative expansion in the coupling parameter, and finally those inflaton decay for a particular decay channel, and we get the radiation parameter.
So wait, this issue is only when the amplitude of the oscillation is small enough.
The issue, actually, when the amplitude of the oscillation is small enough, then actually we treat this perturbative analysis.
Okay.
Otherwise, we cannot neglect the non-perturbative. The resonance production is always there. We need to take care.
Yeah. Okay.
So that is why. So as the inflaton condensate contain the non-vacuum expectation value, so we cannot ignore this kind of resonance production here. But obviously, there are some parameters, ranges like the inflaton and the standard model particle coupling is quite weak. Then always we can do the perturbative treatment. So now let's see that how the evolution of the co-moving Hubble scale changes if we introduce this reheating case. So here we plotted the co-moving Hubble scale, and that you can see that introducing this reheating that changes the expansion history. And as a result, what happens if we, for a particular inflation model, if we just consider the scale, the CMB pivot scale, and just if you calculate the exit point and free entry point, if you connect these two, then depending on the duration of the reheating, it regulates the duration of the inflation. So for a particular inflation model, it changes the prediction, the CMB prediction of the tensor to scalar ratio or the scalar spectral index. So that somehow indirectly related with the duration of this reheating. So that is interesting that the reheating also helps indirectly in constrain the separate inflation model as well. Okay. So just move to the perturbative reheating scenario. this evolution of the density component and how the equation of state parameter evolves. So if you have the different density component, if you consider that the inflaton that decays into the standard model particle, and there is some collision term associated with it, and if you calculate the decay width associated with the inflaton, then we can solve the Boltzmann's equation for the inflaton energy density and as well as the radiation. So the inflaton decays, and so the solution of the inflaton is dilutes into different way, decays into different. First of all, there is a redshift part that depends on the equation of state, that is a to the power minus 3 into 1 plus w. And there is another term that is this associated with the decay, that is e to the power minus gamma t. So after a certain point, when Hubble parameter is equivalent with this gamma decay width, then what happens? Then inflaton field decays exponentially. So we can get rid of from entire inflaton and we'll get a standard radiation dominated universe. So that is the basic of the standard perturbative reheating setup.
So would you call that instant reheating?
Required?
Would you call this instant reheating?
No. This is not instant reheating. That you can see that this is the evolution of the inflaton energy density after inflation.
Yeah.
This is normalized by the scale factor at the end of inflation.
Yeah.
So this is sufficient duration for the reheating stage, because reheating is defined at the point from when you have the standard radiation domination. So this is the reheating point. This is the point of reheating.
Okay, that's not where inflation has ended. That's where reheating has ended.
The inflation ended at that point.
I see.
So here we have started the evolution of the energy densities, and this is the point of reheating when you have the standard radiation domination.
Yeah. Okay.
So reheating end means you have. Yes. Sorry.
That is the credits.
So is there a question? I guess not. No, carry on.
Somebody spoke.
Okay. Is there any question?
I don't think so.
Okay. So when you involve this different energy component, the one thing you have to do that we took one assumptions that to average out the oscillations. So if we took the single oscillations, and if we took the virial theorem, and from there we can calculate that how the kinetic term, the average value of the phi dot square, it depends on the derivative of the potential. So from there we can calculate that equation of state parameter for the standard fluid. We know that equation of state is pressure over the energy density. Yes.
I don't think he had a question. Yeah.
I just muted
Okay.
someone who was coughing.
Thank you. Yes, thank
Okay.
you.
Okay. So the equation of state is here basically depends on the exponent of the potential, how the potential behaves at the minimum. So finally, we'll talk about the effective quotients. Even if we do the non-perturbative analysis, this average equation of state, it will reach this average equation of state values very quickly. After just with the less than 1 effort, it basically reaches these values, average equation of state values. Now move towards the standard reheating setup. In the standard reheating setup, we basically considered some interaction between inflaton and the standard model particles. The inflaton can decay. There is some scattering process can be involved. Inflaton can decay in pair of scalars or fermions, and there are some gravitational production also involved in this. So the standard model particles can be reduced to the scattering of inflaton field to the exchange of graviton. That is also possible. So here are the possible decay with I have written here. But let's move the discussion towards the another scenario where inflaton is not responsible for the reheating, where interestingly the primordial black hole, the evaporation of the primordial black hole, it takes a job to reheat the universe. So what are the formation mechanism associated with reheating? So there are here I put it 3. There are other several possibilities of PBH formation.
You wrote down why were the diagrams all of the possible ones? It looked like there should have been others.
These are the some possible interaction that I have written. There may be other processes.
Okay, all right, thanks. Yeah, so these
that's
you're going to be interested in. Okay.
Because those possible processes we will consider in my subsequent analysis. That's why these are the possible. Okay. So what are the PBH formation mechanism associated formation mechanism during reheating? So there are several possibilities. One, the standard one is that people generally consider that there is a speed breaker term in the inflationary potential. It basically slows down the inflation. So it took ultra-slow kind of phase at the inflation. So people generally introduce a bump or dip-like features in the potential, or there may be some inflection point in the potential. So that leads to an enhancement in the scalar. But why? Because the power spectrum is simply proportional to the phi dot. It's dependent, inversely proportional to the phi dot, and that leads to the enhancement in the power spectrum. And when this overdense region re-enter some later stages, like some radiation domination or some reheating, if it is dense enough above some critical density, that will collapse and form PBHs. So that is the one mechanism that people generally consider that it is connected from the ultra-slow kind of phase.
Mm-hmm.
And in the other cases, the primordial backward can generally produce in the phase of preheating, because during this preheating there is some instability present in the inflaton, and that can lead to enhancement the perturbation, the scalar perturbation. And if the amplification is large enough, then it may be possible that PBH can form. Obviously, there are structures can form, but whether the PBH is formation is possible or not, that depends on several possibilities. Like whether your the collapse time is less or greater than the PBH time scale or not, and also that will depend what kind of collapse mechanism we are taking. So that is a different. So there are other possibilities like the bubble collision during phase transition that can also happen reheating. So that also leads to the PBH formation. So I am not going into the details of the PBH formation here now. So rather I am interested if we assume that yes, PBHs are there after the inflation, it formed in some mechanism. And now what happens if it is ultralight in nature and it evaporates?
Mm-hmm.
So this evolution of the PBHs is depend on the three parameters mainly. So one is the mass distribution. So it can be the monochromatic one, or we can choose the extended mass function. So, but in our initial analysis, we took the monochromatic. So we have a particular mass, not a mass distribution. Then the formation mass. The formation mass in typical mechanism is connected with the horizon size with some collapse efficiency. So we took the standard collapse efficiency from the Cart's paper, but obviously that collapse efficiency is not exactly correct. We can do more rigorous calculation to calculate what will be the exact value of the collapse efficiency. But that will depend entirely how your background evolves. And thirdly, depends on the energy fraction. So the amount of PBH energy density over the total energy density at the point of formation. So that's it. So we need to calculate the evolution of the primordial backward. So one is the mass distribution, then the formation mass, and the beta, the energy fraction at the point of formation. Once we have these three parameters, we can calculate the energy spectrum of the emitting particles.
But wait, these three parameters are quite model dependent, aren't they?
But here in our analysis, we took all as a free parameter. Because here the mean is related with the horizon size.
Yeah.
So it is related at in which place it is forming, at which epoch, at what time it is forming. So it is related.
Yeah.
And beta we choose as a free parameter.
Yeah.
So finally we can connect it with them. So we have a restriction on beta and mean. Now we can connect the particular model and restrict this with the whatever restriction we have on the beta and mean. But here it is a model independent analysis.
Okay.
But once we fix this beta parameter, not fix this beta parameter, but once we know these things, that what will be your mean and beta, we can choose as a free parameter, it is 2, and then we can calculate the energy spectrum of the emitting particles. Now the energy spectrum here
omega was, what exactly was omega in that, or is it just a rewriting of gamma?
Which omega I'm talking about here?
You've written gamma as omega to the 3/2.
Oh, okay. This omega is the background equation. This is the equation of state parameter, in which background PBH is formed.
I can't quite catch the words. It
The
is
background equation.
Oh,
Equation of
dispersion.
the background. Yeah.
Dispersion. Okay, all right, thanks. So the basic parameter is omega.
Basic parameter, not omega. The one is omega, and also it's somehow related with the energy density of the background. So that is related with the particular model, the inflaton energy density. That is also relevant. So
Okay,
not
but
only the
you're taking gamma, MH, and beta as your parameters essentially, or omega, omega rho n, and
this rho is the background energy density because this is the horizon mass, MH. MH is the horizon mass. So it relates with the energy density of the background.
right.
And obviously it is connected with the energy, the equation of state.
Yeah.
So basically we need that in which background equation of state the primordial black holes are formed.
Mm.
Okay, once we have those parameters, then we can calculate the energy flux of the emitting particles. So we can calculate the energy flux for spin 0, spin 1, spin 2. Here I have shown well spinning particle. And in the right side, in the right side, I have plotted the absorption cross section. So this absorption cross section is related with the gravity factor. So what is the gravity factor? Technically, you can speaking, this is the transmission coefficient of the whole from horizon to infinity. So this is related with the transmission. So once we calculate absorption cross section and everything, so we know the spectrum of the particle, emitting particle, and then we need to integrate out this to all over the energy, the possible energy 0 to infinity, because the energy of the emitting particle can be anything. So we'll get an evaporation function. Ultimately, we'll get an evaporation function. And this evaporation function, epsilon, it strictly depends on which kind of spinning particle we are talking. So it for 0, for half, or spin 1 particle, or spin 2 particle can be. But there are some estimation, analytical estimation in the high frequency limit. But in the high frequency limit is only matches with the numerical result for the bosons for spin 0 particle. Otherwise, for the spin half or the spin 1, spin 2, there is a huge deviation. As long as we increase the mass of the emitting particle. Because in the x-axis here we have plotted the mj, the emitting particle mass, over the black hole temperature. Okay, so once we calculate the evaporation function, then the total evaporation function it depends on that if we talk about the production of only the standard model particles, we need to sum over all the standard model degrees of freedom. And finally, we get the total evaporation function. And another assumption we are taking here that the co-moving number density is constant. Co-moving primordial black hole number density is constant. So under this consideration, we can solve the Boltzmann's equations or Boltzmann's equation for the primordial black hole. So now in the setup, so what are there? Now the inflaton is decaying, so there is a specific interaction between inflaton and the standard model particles. So that will give you my decay term. And now the radiation is sourced by the decay of the inflaton and as well as the PBH evaporation, the decay of the primordial black holes. So there is a competition. That there is a decay is happening because we are interested in producing black holes in a inflaton dominated background, and then primordial black holes is also evaporating. So there is a competition, and depending on that, the strength of the coupling, we can say that in some parameter space, the primordial black hole can be the dominating candidate to reheat the universe. So this is the mass reduction rate. Now, what are the restrictions on the primordial black hole when we're talking about the ultralight PBHs? So in the ultralight PBHs, the minimum mass is restricted by the horizon size at the end of the inflation, the rho end. Because we are interested in formation of the black holes in the reheating era. So the minimum horizon size that we can consider that is associated with the end of the inflation. So that gives around 1 gram black hole. And we are interested to evaporate these black holes before BPL, because otherwise there will be several constant on the beta parameter. It will violate, it will produce some extra reduced degrees of freedom and other things. There are some several constant will be there on the abundance of the PBHs. So to neglect to get rid of from those constraints, we restrict ourselves that the primordial black holes are formed during reheating and it evaporates before the BPL. So these are the mass ranges we are interested. So from 1 gram to 10 to the power 8 gram. Another point is that if primordial black hole forms in the very early universe just after the end of the inflation during this reheating phase, that may be possible that this black hole dominates the entire background and then evaporates and forms standard model particles. So if primordial black hole dominates, then there is a gravitational wave, induced gravitational wave associated with those black holes. Because there is a density fluctuations is available in the primordial black holes, and those can lead to isocurvature perturbations. So here there is an induced gravitational wave is present due to the density fluctuations in the PBH, density fluctuations in the primordial black holes, and that from there we have a restriction on the beta parameter, because for high beta parameter it may be possible that it overproduces the gravitation. So from the delta extra relativistic degrees of freedom perspective, there are some restriction on the abundance of the gravitational, and subsequently there is a restriction on the beta parameter as well. So we
And how long do you expect this to go on for, the evaporation of the primordial black holes?
go on for means yeah,
How long? Like so if they are deriving basically the reheating phase, yeah, would it be a slow reheating scenario? Yeah, basically, what would be your reheating temperature? Yeah, that would
okay,
be.
that I'll show. That I'll show. That
Okay,
everything I'll show. The what will be the reheating temperature and what will be the possible duration and what is the maximum temperature we can get from the evaporating black holes. That I'll show. Yeah.
Okay.
So these are the restrictions on the PBH parameters, on the mass and the beta parameter from induced gravitation. Now, once we set up this thing, then there are some possibilities, the evolution of these energy densities. So the left one is without primordial black holes. So you can see that here we choose just considered about 10 to the power Wi-Fi equals to 10 to the power 10 to the power minus. That you can see that here the reheating happens. Just follow the solid lines. The blue one is for inflaton energy density, and the red one is the radiation, and the reheating happened at that point. And the typical reheating temperature is 10 to the power 7G. On the other hand, if their primordial black hole is there with beta value is 10 to the power minus 4 and mass 10 grams, that may be possible that primordial black hole dominates at the early universe and then it evaporates and produce the radiation. So this is the evolution of the radiation energy. This is the red one, and the dashed one is the without black hole prediction. So there you can see that now we get a much higher temperature, so around 4 into 10 to the power 8 G. So from this point, the evolution of the radiation energy density is controlled by the evaporating black holes. So these are the dependency how the inflaton and the radiation energy density sourced by inflaton and the sourced by black hole. It depends on the scale factor. And point to be noted that we only consider here some equal kind of interaction, and definitely we can consider a different decay channel, but the conclusion should be the same. If your temperature is of the order of that, but if you have a primordial black hole with this parameter 10 to the power minus 4 and 10 grams, then we will get much higher temperature. So now for the PBH dominated case, so what happened in the case for the PBH domination? The condition for the this is the beta value we required to dominate the entire background. So if this beta value have above this critical one for a particular mass of the primordial black hole, the formation mass of the primordial black hole, then may be possible that the black holes can dominate and then it evaporates, leads to a standard radiation damage. So here what happened that here the green one is the evolution of the primordial black hole, so it dominates, and then its evaporation leads to radiation damage. The red one is the evolution of the radiation energy. And you can see that after this point, this evolution of the radiation component, it depends on the evaporating black hole, because the dashed one is the without black hole evolution. And so, so only it dominates if the production, if the production rate associated with the primordial black hole is greater than the production rate associated with it. So this is the temperature for this reheating setup, and here for the PBH domination case, it is independent of beta. This only depends on the mass of the black hole, because once it dominates the entire background, the beta becomes 1. So it does not depend what initial beta we are testing. But in the second case, when PBH is not dominating, it is evaporating in an inflaton dominated background. Because here you can say blue is the inflaton one, the green one is the PBH, and red one is the radiation. So this green one is evaporated in a radiation dominated background. In that case, you have a beta dependence. But to get reheating for this kind of scenario without PBH domination, we need a higher equation of state, higher inflaton equation of state. The equation of state associated with the inflaton, the average equation of state, must be greater than 1. So it must be redshift faster than the radiation to get such kind of variance. And there is a critical value of beta that is depend on the strength of the couple. If the beta value is greater than this for a particular choice of coupling, the inflaton standard model coupling, then you will get this kind of variance. And here the reheating temperature depend both beta and the formation mass. Now move to the case where we compare the scenario of the monochromatic mass function with the extended. In the extended case, so there should be a mass distribution. So to get the number density of the black hole, we have to integrate out over a mass range where the distribution function, the mass distribution function works. So APBH means number density of the black hole over a mass range m to n plus del m. And from there, we can calculate the energy density of the. And again, here also, we consider the same assumptions that the co-moving dark matter number density is conserved. And now subsequently the Boltzmann's equation are modified, because here there should be a integration over mass, because we are not considering a particular mass of the black hole. We have a distribution of the mass. We need to integrate out over this distribution, the minimum and the values. And if we just compare the monochromatic result with the extended one, here just we took a sample of the sample the power law mass function from some card paper. So that is the behavior of that mass distribution for different values of alpha. This alpha, it depends on the equation of state parameter. And we can see for if the extended mass function has a sharp peak, then it mimics the monochromatic result. If it has a sharp peak, if we choose the monochromatic with the same mass value, then we will get the same result. But for the violet one, we can see there is a extended this distribution value is same for a extended values of masses. So for this case, we have a difference between the monochromatic and the extended result. There's much difference between the results between the monochromatic and the extended. So here compare that inflaton reheating with the primordial black hole reheating. Just follow the right plot. Here have plotted the reheating temperature as a function of the beta parameter. If we just follow the black one, that there you can see that initially it is independent of beta. So the initial parameter is controlled by the inflaton. So their PBH region is subdominant. But after some beta values, it's possible that reheating is coming from the PBH evaporation. And after some higher values of beta, these values of beta, it's become again beta independent because their PBH dominates the entire background. So it's the beta independent. So the left side from this point, it is dominated by the inflaton, and there it is dominated by the evaporating black holes. So now, once you have this reheating scenario with these evaporating black holes, primordial black holes, then we move the discussion towards the production of the dark matter from a single. So the number of particles emitted by unit time per unit energy scale for a Schwarzschild black hole can be written in this manner. And if you calculate the number of particles emitted from formation point to evaporation point, if your mass of the emitting particle is less than the less than the black hole temperature, then throughout the evolution it will produce that dark matter. So the integration should be from T into T evaporation. But if possible, if your mass of the dark matter is greater than the black hole temperature, then we need to, initially it is kinematically forbidden, but as black hole decays, the black hole temperature increases, then this channel should be open. So the integration is coming from Tj to T. Tj is the point when the mass of the emitting particle is equal to the black hole temperature. And once we have the number of particles emitted from a single black hole, we can multiply it with the black hole number density. And if the reheating point and evaporation point are different, then we need to evolve it to up to reheating point. Then after the reheating, the yield should be same. Yield means the number density of the dark matter over the entropy density. That will be same. And finally, we can connect to the present. So these are the dark matter parameter space for the PBH domination. And we can see that is the beta independent. And similarly for where PBH is not dominating and beta is less than this beta critical value, then there are several possibilities that inflaton reheating also possible. And we have shown here that for different values of Wi-Fi, different values of Wi-Fi, what will be the parameter space for dark matter? Because here standard model particles are produced from both inflaton and the primordial black holes, but the dark matter is solely produced from the PBHs. But there should be other possibilities if we took the dark matter also produced from the inflaton, but we are not in this work. We have not complicated these things. We are only concentrated on the part that the standard model particles have both sources, but in the dark matter side, only the dark matter particles are produced from the evaporating black holes.
So just from evaporation of the black hole, not from gravitational production from the black hole.
Evaporation of the.
Okay.
Simply we took the Hawking evaporation and the dark matter particles are produced.
Mhm.
Okay. So up to this, we have talked about that what is the implications of the ultralight black holes in terms of production of the standard model particles, dark matter. Now, if we talk about some observables like the gravitational wave and how we can decode this phase of reheating with this gravitation. So initially, I'll talk about the primary one. The primary means the tensor perturbation, which is produced due to the vacuum fluctuation during inflation. Then we calculate evolve it to the present day and calculate it today. Now, what happened if it evolves to a non-standard phase? We know that the gravitational energy density is redshift simply as a⁻⁴ at radiation. But your background is evolving in a different way. So depending on the equation of state associated with the non-standard phase and the duration, will have a tilt in the primordial gravitational state. And it will be blue tilted if you have the average equation of state greater than 1/3. And if you have red tilted spectrum, if the equation of state, background equation of state, less than 1. So these are the modes. These are the results for the modes which re-entering during this reheating. And these are the standard radiation. Because those modes are entering during the leaf inflation at some point and re-entering during standard radiation domination. So that's they have no effect of it. So once we have this primary one, let's try to probe the universe physics through this primary gravitational. If one consider the future gravitational emissions like LISA, ET, DC, So if you calculate the SNR, signal to noise ratio, for a particular observation time, I think for the space-based observatories, it's around 4 years, and for the ground-based observatories, it's around 5 years. And the threshold value is also different. It varies from 10 to 5. And if this SNR values is greater than this threshold one, so there is a possibility that it can decay stochastic gravitation. And these are the parameters, the probing parameter or compatible parameters with these observations, LISA, ET, ETC, and B. So Wi-Fi is if you just consider the inflaton decays into pair of fermions, so these are the coupling ranges that can be probed through these feature observations. And similarly, if it decays into pair of scalars, that parameter space also shown here.
And the white regions are not ruled out by any means. They're just not accessible by any of these experiments, right?
The ruled out means what?
The white regions on these plots.
Oh, white region is plots is cannot be probed by this.
Yeah.
That is. So these regions are basically compatible with the observation.
Mhm.
That is our conclusion. And similarly, we can also take the primordial black hole reading, and these are the beta amine parameters that can be probed to these observations. But point to be noted, we don't know that because here we only took the noise curve and with this analysis, but it's just a rough idea that what parameter space can be. Now, let's move toward the stable black holes. So till now, I talk about the ultralight black holes that and how the evaporating black holes can produce the standard model particles, dark matter, and what we can say about the probing possibilities of the early universe through primary gravitational wave. But there may be possible that black holes are large enough that can be stable today. If the mass of the black holes is above 10 to the power 15 gram, those black holes are termed as a stable black. And in the first phase of my talk, I did not consider any formation mechanism associated with the black hole. But if one consider a particular formation mechanism, like the black hole are formed through this USR kind of module. Let's say there is an ultrasolar kind of phase at early during inflation, and that can lead to enhancement in the power spectrum. For those scales, this lambda PBH, very small scales compared to the scales of the same beam. And when those if the enhancement happens during these scales, the scalar perturbation, and when those overdesk region re-enter during some later stages during reheating or the radiation domination, that can form depending on the how much density. So this is the basic formation mechanism we are interested that coming from the USR. And what are the scales we are interested in? We are interested in the small scales around this, and the amplitude of the scalar perturbation that needed to form PBHs. This is the range that above 10 to the power minus 2, close to 1. At least this large amplification needed to form PBHs. So this is a very fine-tuned process.
So when you say they're stable, meaning that they will contribute to dark matter reluctancy as well?
Yes. So in the first part of my talk, I am interested in the evaporating black holes. So now I am talking about the black hole mass above 10 to the power 15 gram. Those black holes are stable and can be treated as a dark matter. Okay. And another interesting thing is that if we consider a particular formation mechanism associated with it, like USR kind of phase is there, and there is some enhancement in the scalar spectrum, those can lead to a induced gravitation, the scalar-induced gravitation. Yeah. Because in the first scenario where I described this, the primary one, I consider only the tensor perturbation without any source term. But now, as we know that at a linear order, the tensor perturbation, scalar perturbation that independently. But at the second order, the tensor perturbation can be sourced to the scalar part. Tensor perturbation can be sourced to the scalar perturbation at the first order. So that's we are taking, and in that case, we are getting some enhancement in the gravitational wave. Because technically, if you have a scale invariant scalar power spectrum, the amplitude is lies above around 10 to the power minus 22. And for the primary one, it is depend on the energy scale of the inflation. So if for the large scale inflationary model, if your Hubble parameter at the end of the inflation is during inflation is around 10 to the power 13 GeV, then it typically comes out 10 to the power minus 17. So it is subdominant. But as there is a enhancement, a smaller scale, enhancement is the scalar perturbation at the smaller scale and huge amplification, because we need to form primordial black holes as well. So that leads to an enhancement in gravitation. And here we try to compare the compatibility of this kind of secondary gravitational wave, induced gravitational wave, with the nanograph linear data. So before that, just I will talk about that how we calculate the PBH in those things. So in order to do this analysis, we need a power spectrum or the scalar power spectrum. So we basically parameterize this scalar power spectrum as a broken power law. So it has a scale invariant part, and as well as there is some amplification part. And ascending part we consider k to the power 4, because most of the USR model, ultra model, is giving a k to the power 4 kind of behavior. But in the descending part, it we've just put as n0 is a free parameter, and finally we try to constrain it from the observations. Okay. So once we know the power spectrum, the scalar power spectrum, and the density contrast we need to form PBHs, we follow the paper by Harada and Khoury, the analytical expression, how the density contrast depends on the background equations. And then finally calculate the FPBH. What's the FPBH? FPBH means the black hole energy density, primordial black hole energy density over dark matter energy density today. So FPBH 1 means your 100% of the dark matter can be from the primordial black holes. Okay. So this FPBH is solely depends on TRE, the background dynamics, the reheating temperature, TRE, and the background equation of state WI, and as well as the formation. So here, and also the K peak values, because it's sensitive to the K peak. So here we just try to see how this FPBH behaves if we change the parameters like the K peak, TRE, and the WI, because it depends on the 3 parameters. And that is important because in the secondary gravitational wave, induced gravitational wave, one of the problem is that overproduction of the dark matter. So FPBH calculation is very important, because otherwise you get one parameter space which is compatible with the nanograph observation, but there may be problem is coming from the overproduction of the dark matter. So that's why you need the FPBH calculation. And we also consider there are several restrictions from the lensing and the gamma ray observations. Those are clear. So once we know the spectrum, and as I mentioned, that we consider that scalar-induced gravitational wave, that means the tensor perturbation at second order sourced by the scalar perturbation, the first order. Okay. And in that case, you do the MCMC analysis by using the PTR kit, the K-field mode. And here we took the 4 different models. In the first case, this is a 4-parameter run. It's a free run. So basically, we change the K-peak values from certain 6 to 9. And you can ask me that why we choose the 6 to 9, because we are interested in the nanograph band, nanohertz band. So so your K-peak value should be lie in the 10 to the power 6 to 10 to the power 9 megaparsec, 10 to the 9 megaparsec. So the 6 to 10 to the 9 megaparsec. And this is the amplitude that we know that at least to form a PBH, we need the amplitude above 10 to the 1. And this is the variation for WRE, the background equation of state, and N0. It also varies the descending part of the power spectrum, scalar power spectrum. So in the 4 parameter free run, these are the best fitted values we are getting. Now in the second case, in the first case, we observe that it is nearly independent of the N0 values. So we choose the N0, fix N0 at the mean value, that minus 2.26, and then we do the 3 parameter, and we are almost getting the same results. The mean value and the equation of change also lies about 0.5 to 0.6 in between that. But now if we do the bound run means we took the constant from the FPBH. So here we connect Kp A0 with the FPBH and mass of the primordial black hole. And then if we do the efficiency analysis, and there for 3 different set of delta C. So as I already mentioned, we initially use the analytical expression for the density contrast from the Harata's paper. But now if we just took some error bar in that maybe 0.5 delta C article to 1.5 delta C article, that how the our result is sensitive with this the analytical expression that we have also checked. But in the 3-parameter bound run, here it also varies PBH from 10 to the minus 20 to 1. But what happened for the bound run or 2PB run? Here we took only varies M, the mass of the primordial black hole and WRE, and took the FPBH bound, whatever it has from the lensing and the gamma ray observations. So we are not varying FPBH. The restriction is already we would include there. The FPBH has some restriction depending on the mass of the mass dependent restriction that we incorporate and do the parameter. It's the power. And these are the results. So if we plotted the marginalized postulate distribution of the parameters, and that we arrive comparing this nanographic data, that is our result, and that we can see that is delta C 0.5 delta C analytical is marginally satisfied. So FPB is very close to 1. But as we increase delta C value with the delta C analytical and 1.5 delta C analytical, we have a wide range of possibilities. And similarly, this is for the R32B run. Means here we fix FPBH, so whatever constant, mass dependent constant. Now, if we plotted with the base fitted values, here I have shown if we just project the result in the sensitivity on the nanogram, the violin kind of sensitivity, then how it looks. And as usual for 0.5 delta C article, it's not fitted well. Similarly, in the right plot, we saw how the for the base fitted values, what will be the FPBH, how the FPBH value with respect to the mass. So then you can see for the free runs, there is a dark matter overproduction, FPBH greater than 1 as usual. But in the 3 PB runs and 2 PB bound runs, where we took the constraint from the FPBHs, and there it is consistent. FPBH is consistent. And point to be noted in all the analysis we took, the reheating temperature is around 15. Why you need that? Because we want the peak value, the peak of the spectrum at near the nanohertz frequency, the nanogram band. So that's why there is a limited choice of the TRE from 1 MeV to 10 MeV to 100 MeV. So we took just at intermediate value to fix at a 15. The reheating temperature is very good. So if we do the basis analysis and calculate the marginalized likelihood for our model and utilize and then evaluate the base factor, against the reference model is the supermassive black hole binaries, then these are the base factor. For the 0.5, it is almost identical. But for delta C analytical or 1.5 delta C analytical, this base factor is quite high. So it basically it is strong based on evidence in favor of our model. Now, so here I have shown that how the stable black hole play the role in the production of the dark matter, because it can be stable, act as a dark matter, and as well as how the gravitational can constrain the history of the early universe. Now, if you just move, I'll mention this on to mention this thing, that how the quantum correction on the evaporating black holes may be interesting, because because once I consider this kind of correction, we are getting the ultralight black holes can be stable, even 1 gram black hole can be. And why this correction needed? Because all the Hawking evaporation is calculated under the semi-classical approximation. And after a sufficient evaporation that may be possible, the emitted particle back reacts. So this back reaction effect can be taken into account. So this basically slows down the evaporation. And how much slow down? And after which point that we don't know. So we parameterize these two things. So Q is the parameter which indicates the after which point this memory burden effect will start. And S and how much reduction in the dissipation rate, that is depend on the entropy, black hole entropy to the per some power. The power is represent the strength of the correction. If you have the higher correction, then it may be possible that one black hole can be stable. And these are the ranges. Now new mass window is open for the stable black hole. So previously I have just shown that after 10 to the power 15 to 16 gram, black hole can be stable and act as a dark matter. But now it is possible that even the small mass black holes like 1 gram to 10 to the power 9 gram, this mass window is open and that can be acted as a dark matter. And what is the K value is needed for such kind of scenario? These are the K values. This is the correction factor, the strength of the correction K, and this is the M in the mass range, and these are the white region are the regions for the stable black. And these are the regions which is evaporated before BBN, and these are the restricted region because those are evaporated by BBN. So evaporated after BBN, so there are several cosmos. So once we calculate this thing, we have a modification on the dark matter because now what happened at the same black hole, the lifetime get increased. So in the PBH domination case, the duration of the PBH domination got increased due to this memory burden effect, and that will generate an extra entropy injection in the system, and that leads to a higher mass to achieve the correction. So this way, as we increase the K values, the higher mass of the black hole, higher mass of the emitting particles actually are compatible with the correction. Okay. So here we have shown how the evaporating black hole and the stable one are play the role depending on the K values. So if we just change the K values from 0, this is the standard case. So from 1 gram to 10 to the power 9, the whole ranges are for the evaporating black. But now if we increase the K values, in all cases fixed Q is equal to half. So after half-life, this memory burden case will start. So in that case, there is some rest for the stable black hole, but those are restricted from the gamma ray observation and the same velocity. But if the K is equal to 2, there is some sufficient region for the stable black. And at increase, it increase for K is equal to 2. So for K is equal to 3, almost we are getting everything from the stable. But there is interesting because as you already mentioned, we don't know from which point this kind of correction will start. If we just parameterize this Q value in very low values, like that after 99% decay, this memory button decay will start. In that case, we have the contribution from the evaporation plus we have contribution from the stable black hole. In that case, from a certain mass ranges, from 10 to the power 8 to 10 to the power 6, we have contribution from the evaporating. Otherwise, all are from this is independent of mean. That means here the stable black holes are the leading. Okay, so that's all. I finally want to conclude my talk. So I have discussed a new background dynamics depending from the possibilities that the primordial black holes form in the early universe after inflation. And here the two possible scenarios. I have discussed two possible scenarios. In one case, PBH itself dominates and then it evaporates and leads to production of the standard model particles. In the other case, I have considered where the PBH is not dominating, but still there is a possibility, depending on the choice of the coupling you have between the inflaton and the daughter fields, there is a possible that PBH evaporates in an inflaton dominated universe, and still it managed to produce all standard model particles. And then move our discussion to the production of the dark. In the case of the dark matter, we consider the dark matter production solely from the PBH evaporation, but the standard model particles can be produced from inflaton and the black hole as well. But here there is one limitation that we are only consider the one channel for the dark. It may be possible that dark matter can be produced gravitationally. That we know that we can that we considered. And another thing is that the inflaton can decay, or from the thermal bath, the dark matter can be produced. So that we have not taken into. So these are the restrictions. And in the third point, we have considered that how this PTA data, the pulsar time array data, can shed light on the universe in the context of the scalar-induced gravitation. And when talk about the scalar-induced gravitation, those gravitational weight associated with the primordial black hole formation. And finally, I conclude my talk by elaborating this fact that even the small mass black hole can be stable as today and can be treated as dark matter. if you have some quantum correction in the evaporation process. So these are okay. Thank you very much.
Thank you very much. Thank you, Riajul. Yeah, that was really good. And wow, it's a lot of information.
Actually, I try to cover the entire perspective of these
And
black
you
holes
covered
from
so
the
much. Yeah. Oh, you
from
covered
the
a
ultralight to the stable one, because all are responsible for the production of the dark matter.
Mhm. Yeah. So, could you go back to your previous slide?
Mhm.
You might have mentioned it, but what are the spikes from?
Okay. So
sharp-
here what okay. So here what we have considered in that scenario, what happened that the primordial black holes initially start with the Hawking evaporate due to the Hawking evaporation process, but after some fractions, there is a memory burden phase and it slows down the evaporation process. But due to the initial stage, there are some dark matter is there. So the entire dark matter component is coming from the evaporation as well as the stable black hole. So here we try to compare that in what mass ranges. Like if we consider the MJ around this range, then the entire contribution from the total dark matter is only coming from the evaporation. The stable black hole contribution should be subdominant. That is the conclusion. So a PBH cannot be 1 in that point.
Yeah.
So more peaks, the large peak means your FPBH should be less than 1. Then higher peaks means you are lowering the FPBH.
Yeah. Okay. Very good.
Riaj, I have a question to ask, if that's okay.
Yes, yes.
In case of astrophysical black holes, we usually know that they are dominated by matter and things like that. And if we are taking into consideration that we are able to calculate the critical points and the sonic points for astrophysical black holes. Now, if we talk about the primordial black holes, we know that it is mainly matter dominated, right? And during the time of reheating, there will still be domination of matter, or there might be matter accreting onto those.
No. Actually, the PBHs are in a W dominated background. Then maybe the radiation background is there. But it may be possible that PBH dominates, then you can get in that way the matter domination. But otherwise, this is dominated the background by radiation or in any inflaton background possible. The PBH can
So if there is matter in PBH, okay, suppose that like there is presence of matter in the PBH, is it possible to calculate those sonic points and things like that for the PBH as well? And how will it be different with respect to the astrophysical black holes?
Okay, so I don't know much about accretion perspective, but yes, that is possible because it can accrete matter, but I don't know that that small mass black hole, how it the accretion physics works here. But it may be possible. Yeah.
Okay, all right, that's fine.
Yeah, so as you said in the beginning of your talk, there's a big gap between the inflation scale and the PBN, and you could fit in many models in there. But yeah, it seems gravitational waves is the only probe we have of that region.
Yes. But here I have not introduced some of the gravitational sources. Like I mentioned that the PBH domination can lead to a, because there are some density fluctuations in the PBH number density that can also lead to a source the induced gravitation. So that is important also in probing the early universe.
Yeah, but the gravitational production of stuff seems to be subdominant here, right?
The gravitational production, yes, because Now, first of all, if the gravitational the subdominant, obviously that will depend on the black hole mass and beta parameter. If your beta parameter is very small, then possible the gravitational production dominates.
Yeah.
So even it's possible that there are some ranges where the gravitational production. So you're talking about the gravitational production of the dark matter from inflaton all the standard model bar.
Yeah.
Yeah, maybe in some ranges that will dominate, but that need to check.
Yeah.
Because as I mentioned, I took beta as a free parameter, so it can be anything. So for small beta values, it's obviously possible. So there may be some, but in the dark matter production, I only consider the production from the evaporating black. But there may be several channels and give a new direction of dark matter person. That I have considered.
So what got you interested in looking at this particular thing? Well, primordial black holes, I guess, are popular, but yeah, I'm just keen to
Okay,
see.
so I am interested in that the probing this early universe physics.
Yeah.
So one of the perspective is that if you have the primordial black hole, so then the possibilities is that there are several sources, gravitational sources associated. So that we can say many things about the early physics. Otherwise, well, like I said, in the technically during this preheating, they are also gravitational wave cancelled because there are some enhancement in the scalar perturbations and that can lead to induced gravitational. I think the Figuera, I think that group, I think wrote some papers about this induced gravitation. So those are also interesting in this direction. So somehow we need get some higher amplitude in the GW, and that is possible either way. You have some non-standard phases that, as I have mentioned, that here, one second. Here what happened? That here the tensor perturbation without any source term, but you have a non-standard phase. The duration is from here to here. This is the end of the image. But due to this non-standard phase, your gravitational wave energy density decays as a to the power minus 4, but your background decays as like initial, a to the power minus 6. So we finally at the present we get a tilt. This is the blue tilt we are getting. So that gives rise some probing process. So this is the one of the things. And the other way we can do that, we can we can formulate a model like some axial inflation model or some other some models can give the tilted tensor perturbation. So here in the standard Slorol models, you always have the tensor perturbation scaling value. But if you have the tensor perturbation, which is have some tilted, blue tilted, then this also gives some possibilities of probing this early. Other than that, we need some primordial black hole stuff and we need some induced gravitational wave associated with it. So I am just exploring that how we can probe this early universe physics, because I think the next 15-20 years this is important, I think, for the perspective of the gravitation. So that maybe to look at.
And could you comment a bit more on, in the literature, it's the perturbative analysis that's been done. You did mention the importance of doing the calculations non-perturbatively, but yeah, I lost.
So one of the importance that I already mentioned in one of my work, actually, I have done this thing, that what happened if the inflaton rolls down the minimum of the potential and oscillate like in the phi square kind of behavior, if at the minima, the behavior of the potential is phi square, then what happened if you do this non-perturbative treatment, you cannot get rid of entire inflaton at all. So you'll get you'll get a saturation at the equation of state like 0.2, then finally inflaton dominate in the long run. So you cannot get rid of from it. So finally, you need some perturbative treatment. You need this perturbative expansion in the coupling parameter and do this. And another important thing is that for the higher equation of state, like equation of state, like the 5 to the power 8, 5 to the power 10 kind of potential and the minimum, in that case also, this parametric resonance is subnormal. I think there are some papers, but Amina also they I think some papers, and the results suggest that after 5 to the power 6, 5 to the power 8, I think those kind of potential cannot lead the parametric resonance. So their perturbative treatment is the only option.
Yes, Very good. Thank you. It was a really informative talk.
So is there any other question?
It doesn't seem to be. Anybody else? Questions? Comments? If not, maybe Denjo, you could stop the recording.
Yeah, I'll stop the recording. Okay, thanks.
Yeah.